right, we are about to begin chapter 5, and you've heard me talk a little bit about proofs in the past, and I'm kind of going to give you the precursor that these next two sections kind of lead us up through proofs. So we're going to start section 5.1, using the fundamental identities. When we get to 5.2, it's going to be more of the proofs, although you see a little bit of the proofs in this section. But what I want to stress is, before we get going, all right, pause the video, go to page 340 in your text. There are fundamental trig identities. You are going to want these in your notes. You are going to be using them on almost every single problem. I would pay particular attention to the reciprocal identities, the quotient identities, and the Pythagorean identities, as those are ones that we've already used in this course, and we are going to be using more in depth. Not a ton of them on this, because we've actually seen this problem before. This first one is a little bit of a review. If they give you secant u is equal to negative 3 over 2, and that tangent u is greater than 0, we've already done this problem. So the way I look at it is we know r and x, and of course if we know r and x, we know x squared plus y squared equals r squared. So what I know here is negative 2 squared plus y squared equals 3 squared. Of course, I knew the 2 was negative because r can never be negative. So I could figure out that y squared is equal to 5 by subtracting 4 to both sides. All right, so I get this idea that y is equal to the square root of 5, but I have to be careful. They gave me this tangent is greater than 0 for a reason. Well, if I conclude that I knew x was negative, well, for tangent to be negative, tangent being y over x, then I know both of these are going to need to be negative values to overall be positive. So, conclusions, I would know sine as negative radical 5 over 3. Cosine, just the reciprocal, would be negative 2/3. Tangent, y over x, that's going to be negative, because it's positive. Tangent, theta, and actually they used u in this problem. So we would have, let's see, negative radical 5 over, did it again. Sorry about that. We would have radical 5 over 2. And then you just have all your reciprocals. So cosecant, negative 3 over radical 5. But we would simplify to negative 3 radical 5 over 5. And then we also need cotangent, which is 2 over radical 5, and then we simplify that, that would be 2 radical 5 over 5. Okay, but like that, that's more of a warm-up problem. This is where we're going to start getting to using our identities to simplify, and these are tricky questions. So, what the idea here is to really focus on those notes that you've taken off of page 340, and what do you see you can do? And there's a number of strategies that we can look at, looking to simplify, and here, the way that I start to see that we can simplify is we can factor. And one of the tricks is you're going to look to factor. And actually, one of the skills that we want to build today is being able to factor using trig identities. It's a little different, but if you notice, this is essentially a binomial. So it's two terms, and both of the terms have a sign in them, so I can factor out a sign. What does that leave me with inside the parentheses? Cosine squared x minus, and I need a placeholder, so I need to put a 1 there. All right, so now I've got to start, but again, I think I could probably simplify a little bit further. And here's why the Pythagorean identities are so tricky, because everyone remembers the Pythagorean identity, sine squared plus cosine squared equals 1. So this is the Pythagorean identity that we already know. Everyone remembers it this way. But it's not the only way you can use it, because I could subtract, for example, I could subtract... There's several ways to write this here, and this is where it gets a little bit tricky. So I could subtract cosine squared x to both sides. Cosine squared x to both sides. And now I have this other identity. Now, we don't usually remember sine squared x is equal to 1 minus cosine squared x, but it's easy to remember from the Pythagorean identities. Now, here's the tricky part. What I put in green right here doesn't quite match up with this right here. They're close, but if I look, this cosine right here is actually positive. This cosine right here is actually negative. I got negative 1 right here. I got positive 1 right here. So what I'm noticing is all my signs are different. And the easiest way to deal with that is if I factor out a negative 1, going back to this statement, if I factor out negative 1, that's going to change all my signs. So I'm factoring out negative 1. I already factored out sine x. And now this cosine squared that was positive is now going to be a negative cosine squared. And that minus 1 is now going to be plus 1. So now what I've got here matches up exactly with what I've got here. So I could make a replacement. This is where a substitution could come in. So I could actually substitute. So keeping the negative 1, and right here I'm just going to write this as negative sine x. That's easier. And I know that this negative cosine squared plus 1 is the same as sine squared. So I could simplify this completely down to the opposite of sine cubed x. These proofs are tricky. The strategy here that I'm hoping that you see is 1, look to factor, and 2, start to realize that this Pythagorean identity of sine squared plus cosine squared equals 1, that's not the only way to write it. You could do some operations to both sides and have a couple different Pythagorean identities from each one of these. And we're going to see that as a little bit of a theme today. All right, so here we're going to, now this is really a proof where they say this part on the left, start with this and prove that it's equal to the right-hand side. Now, some of us in class have tried to do operations to both sides. As these problems get harder, that strategy is going to be harder and harder to use, and you'll be less and less successful. So I'd like you to try some of the ideas that I'm going to bring about. Like 1, looking to factor is one of them. Of course, there's nothing here that's factorable. 2, I do see fractions, and we are going to try to add these fractions. So to try to add fractions, you need common denominators. So if I look here, I need to get these two. So I'm really going to forget about this left-hand side right now. I'm not even going to pay attention to it. I'm going to hope that my answer comes down and eventually simplifies to cosecant theta. But we'll worry about that later. To get common denominators, I'm going to need to multiply this first fraction by sine theta over sine theta. That's going to make my first denominator sine theta 1 plus cosine theta. All right, that means this second one, I'm going to need to multiply by 1 plus cosine theta over 1 plus cosine theta. Again, multiplying by a form of 1, which is what I've really done, doesn't change the value. I'm just changing what it looks like. So I'll simplify the top right here. That's sine squared theta over, and I know my denominator is going to be sine theta, parentheses 1 plus cosine theta. And now it's plus. All right, here I'm going to do a little distributive property. I'm going to call that cosine theta plus cosine squared theta, all divided by same denominator, 1 plus cosine theta. Now that I have the same denominator, I'm going to be able to write this as just one fraction, and I already know the denominator because when I add fractions, the denominator stays the same. And on the top, excuse me, on the top, I already noticed something. I'm seeing sine squared, and I'm seeing cosine squared. And that immediately triggers something that you should notice from your notes. All right? Hoping that you are thinking Pythagorean identity. In fact, it's the Pythagorean identity we saw on the very last slide. All right, so in your notes, you should know what the green rectangle is equal to. That is one of our Pythagorean identities, probably the most important of the Pythagorean identities. We are going to replace it. It is equal to 1. So we are going to replace, sine squared theta plus cosine squared theta. All of this is equal to 1. So here we go. 1 plus cosine theta is now the top of that fraction, right? Because all the sine squared plus cosine squared we know is equal to 1. The bottom is sine theta, parentheses, 1 plus cosine theta. All right, so on the top I have a 1 plus cosine theta. On the bottom I have a 1 plus cosine theta. Those are able to be canceled out. And what I can simplify this down to is 1 over sine theta. And at this point, now I start thinking about that end of, oh, they asked me to show this is equal to cosecant. Well, there's not even really any work to that because by the reciprocal identities, 1 over sine is the same as cosecant. So as you can see, these proofs are getting a little bit more complex than what we were doing last chapter, but they focus heavily on those notes from section 340. On almost every problem you're going to be using one or more of those identities. So here's some of the very straightforward factoring. Now, I look at this and I see two terms, and I go, there's only a few ways to factor two terms. All right, it's essentially a binomial. Either there's a common factor, like a GCF, or it's a difference of squares. And there's no GCF, so if you're asking me to factor, I'd have to use difference of squares. So I'd be thinking, does this look like a difference of squares? Well, it's already got the minus, that's the difference two-part. Secant squared, well, that's just like x squared. And 1, I know that's a perfect squared. So this is going to this would factor to secant theta plus 1, secant theta minus 1. And that's about as easy as a factoring example as you're going to see. There's no further simplification. It's completely finished. But it's that idea of it's different than working with x's, which you may have used in the past. But if you can factor x squared minus 1, you can factor secant squared minus 1. It's really no different. All right, here we go. Trinomial. You've heard me say it in the past. I see three terms. First term, second term, third term. When you see a trinomial, you've factored trinomials in the past. If you prefer to think of this as 4x squared plus x minus 3, if you can factor the top, it's not a whole lot different. So you have to do a little bit of guessing and checking here. But when we go to factor, let's say we either know this either has to be, well, usually you would put an x and an x, but here we're going to put a tangent theta and a tangent theta. Of course, tangent theta times tangent theta is only tangent squared theta, and I need to be 4 tangent theta. So you could either try 2 and 2, or you could try 4 and 1. Let's see if 4 and 1 works. If I put down 4 and 1, then I know my last two pieces have to be a positive 3 and a negative, or so a positive, let's see, negative 3 and a positive 1. I can check that by doing a little, that's negative 3 tangent theta. Over here, that's 4 tangent theta. I know that adds up to tangent theta, which is exactly what I'm looking for to add the tangent theta. Those match, so I have factored correctly. The circled part in green would be the correct answer.